Hola, buenos días a todos.
Good morning, everyone. Thank you for being with us today and joining our sessions in this third day of our seminar connected with the use of recycled material in roads. We're going to start with the first session of our third day. As I was saying, this is a technical session where we're going to share 3 presentations from our colleagues Gina, Edgardo, and Thierry. We are going to continue with the same dynamics that we used in the previous 2 days. We are going to hear the presentations from the 3 presenters, and at the end we're going to open the floor for a Q&A session. And before we start, we want to remind you, or there's a reminder from the organization, that there's an icon in the platform for a survey, so we will please ask you to complete the survey. And also, in the case of the questions for the Q&A session, please don't enter your questions in the chat, but use the question and answer box, because that facilitates our job. So without further ado, we're going to introduce Gina Ahlstrom, who's a civil engineer. She has a master's in civil engineer. She's a leader in pavement material in the building area in Road Building Association for the United States, and she's going to talk about Economical Concrete with Recycled Concrete Aggregates, providing broader sustainability benefits in Texas.
Liz, if you are ready, please, you can start with your presentation.
Good morning. Good morning from the East Coast of the United States. I'm happy to be here. Again, I work for the Federal Highway Administration, or FHWA, in the United States. Today, I will be presenting a case study on recycled concrete aggregate from the great state of Texas. In this presentation, I will discuss the motivation for this project, the approach the Texas Department of Transportation took, a brief discussion on the fundamentals of sustainability assessments, the performance of the project, and finally, key outcomes from the project. In the 1990s, the Texas Department of Transportation struggled with a lack of suitable, locally available aggregate sources and rising costs of virgin materials. At the same time, Texas was experiencing a few performance issues with virgin aggregates in its continuously reinforced concrete pavement, or CRCP, designs. Given the growing availability of concrete for recycling, Texas began exploring the use of recycled concrete aggregate, or RCA, in infrastructure projects. However, one challenge in using RCA in CRCP was a limited understanding of the mix design requirements and the impact of RCA on long-term performance. To gain a better understanding of RCA usage in CRCP, Texas looked to incorporate it in the 1995 reconstruction of a roughly 9-kilometer section of Interstate I-10 in the Houston metropolitan area. The original CRCP was built in 1968 and exhibited significant distress after nearly 27 years of service and under very heavy traffic loadings. The contractor elected to use 100% RCA in the concrete of the new CRCP, primarily as a cost savings measure. The project was unique because it was one of the first in the nation using 100% RCA, that's both coarse and fine materials and contained no virgin aggregate. As part of this project, Texas performed a comprehensive study to address the concerns regarding impacts on fresh and hardened concrete properties, as well as CRCP concrete performance. Evaluation of the environmental impacts was done recently as part of ongoing efforts under FHWA's Sustainable Pavements program. This slide shows the two typical pavement sections used on this project. Note that one section of CRCP was constructed with a double mat of reinforcement, which is fairly typical in Texas. The second section is a concrete overlay, which was a new CRCP section placed over an existing and older CRCP section. No information on the specific mix design that was used for the project is available today, other than the requirement for a 6-sack concrete mixture. Texas also required that the RCA conform to the same specification requirements as virgin aggregates. Testing of the material to evaluate its properties and characteristics had to be completed by the contractor. This table shows the properties of the RCA aggregate used on the project. In the case study report published by FHWA, Texas results are compared with typical values for conventional virgin materials of gravel or silicious sand. At the start of the project, the contractor had difficulty producing a concrete mixture with consistent workability and strength. It was determined that low strength was the result of inadequate moisture control of the RCA stockpile, and this was mitigated by installing a sprinkler system for the aggregate stockpiles. Due to construction issues related to inconsistent and premature concrete setting during placement, Texas changed its specifications to limit the amount of RCA fines in concrete mixtures to a maximum of 20%. This is consistent with current practices today that commonly limit the maximum amount of RCA fines to no more than 30%. In order to determine performance of a sustainable practice, we should look at the 3 legs of the sustainability stool: economic, environmental, and social. For economic evaluation, we can use tools such as life cycle cost analysis. For environmental impacts, we can look at life cycle assessments. Various rating tools such as FHWA's INVEST or tools such as Green Roads can be used to assess the social impacts. It is important to note that life cycle cost analysis and life cycle assessment are very different. For an LCCA, the economic impacts over the entire life cycle of your pavement are assessed or analyzed. This considers initial construction costs, but also costs over an analysis period, such as 40 years, that considers maintenance cycles. For an LCA, the environmental impacts are quantified. The outputs of this analysis are in terms of impacts such as emissions, global warming potential, resource depletion, and so on. This is a graphical representation of an LCA. LCA inputs are materials, energy, waste, emissions, and transportation. These are calculated across the various life stages that you are evaluating: the materials and energy for the acquisition of the raw materials, the materials and energy for the materials processing. This would be where recycling is a factor, and so on. This analysis would continue through the manufacturing, use phase, and end of life of your pavement in this case. The analysis results in an results in an output in terms of waste and emissions, which can be translated to impacts such as global warming potential, which was mentioned on the previous slide. A simple example to demonstrate the benefits of a sustainable practice can be illustrated by comparing the use of paper bags to plastic bags. We may think that it's better to use paper bags. They decompose and can be recycled, correct? When we think of plastic, we may think of it in terms of the picture here, where plastic pollutes our environment. But in order to fully understand the environmental impacts, we should conduct an LCA, where we may find that the depletion of a forest has more of a negative impact than the use of plastic. Performance is a critical consideration for any sustainable practice. To evaluate the in situ properties of the concrete containing the RCA in Texas, 15 cores were taken throughout the project shortly after construction. The test results are summarized in this table. In general, the strength values were noted to be lower than typical values for concrete with virgin aggregates, but the RCA concrete did meet the Texas specifications. Petrographic analysis of cores taken from the CRCP revealed a good bond between the original silicious river gravel aggregate and the old mortar, and between the old and new mortar. Additional testing performed on extracted cores revealed that the modulus of elasticity of RCA concrete is much lower than that of virgin aggregate concrete. The coefficient of thermal expansion for RCA concrete is similar to virgin aggregate concrete. The chloride content of RCA concrete is higher than virgin aggregate concrete, while sulfite content is comparable. The density of RCA concrete is lower, and water absorption is higher than that of concrete with virgin aggregates. Yet, RCA permeability was still classified as very low per ASTM standards. Since its construction in the mid-1990s, the performance of this pavement has been very good. An average crack spacing of roughly 2 meters was reported in 1999, along with crack widths in the range of 0.02 centimeters to 0.07 centimeters. These cracks are very tight, although there is some variability of the crack widths within individual cracks. One very positive performance observation was the absence of meandering cracks and crack spalling that has afflicted many CRC pavements in Texas that were constructed with silicious river gravel, which was the coarse aggregate in the original recycled concrete. It is hypothesized that the low modulus of the RCA concrete and its strong bond between the RCA and new mortar are key factors in its favorable performance. This table provides a summary of the IRI performance data that was collected between 2011 and 2016. Over a 5-year period, the IRI values remained in a good and fair ride range. In terms of sustainability performance, it is estimated that $1.4 million was saved. Almost 208,000 tons of virgin aggregate was saved, and over 1 million pounds of CO2 equivalent and global warming potential was saved. From this project using 100% RCA in a continuously reinforced concrete pavement, we can determine that this pavement performed with good service levels for more than 10 years. It is beneficial to limit the fines to 20%. RCA moisture must be controlled. Sustainability benefits can also be realized. There are reduced costs associated with landfill of materials and extraction and processing of virgin aggregates. There is a reduction in the depletion of virgin materials. There is reduced global warming potential. It is important to quantify the sustainability benefits. The mission of FHWA's Sustainable Pavements program is to advance the knowledge and practice of designing, constructing, and maintaining more sustainable pavements. We do this through stakeholder engagement, education, and developing guidance and tools. We have many resources that anyone can access. For example, more information on the case study presented today can be found in a published document. We have many other tools such as a reference manual, technical articles, and LCA tool development. You can access these resources through FHWA's website by simply entering into your search engine FHWA Sustainable Pavements Program. Thank you.
Thank you, Gina, for your excellent presentation. Please stay connected because at the end of the session, we have time for questions. Y en este momento.
And now, we are going to have our second presentation. In this first session of the day, the presenter is going to be Edgardo Becker. Edgardo is a construction engineer on the Universidad Nacional del Centro from the province of Buenos Aires. He is development and technical service manager at Loma Negra, and he is going to present his presentation that is called Performance Improvements in Rigid Pavements with Recycled Concrete Aggregates. So, Edgardo, you have the floor if you're ready, and welcome. You are muted. Thank you very much. Good morning, everybody. I'm going to share with you my paper about the use of aggregates produced as from old concretes or concretes that are no longer in use, and that this is not just a good idea from the point of view of sustainability. We have already had presentations on that, but it may be quite convenient from the technical point of view, and in certain solutions, as in my experience, I've seen it, they are even better or provide a better solution in certain situations compared to the use of conventional aggregates. My presentation, it's basically divided into three parts. First, I'm going to have an introduction on the evolution of tensile strength, induced stress, and how they act on the concrete and the concrete pavement. And then we are going to discuss an example using recycled aggregates and how this has a positive impact in concrete pavement behavior, and then the conclusions at the end. So, as the dilation reactions of cement particles evolve within a concrete mixture, we have an evolution of the compression tensile strength, and we don't have to forget that at the same time we see an evolution of tensile strength And from the point of view of the conventional that is not negligible, but from the point of view of a GPCP payment, this is an essential parameter. Though many times we don't measure it, it is an essential, a critical parameter for the behavior of those payments. Basically, if we, no, I'm not going to enter into details, but basically if we can see that there are induced stress, and when there are tensile strengths, when they evolve, and when they evolve and get to the threshold of the tensile strength, we have crackings. And those are the ones that we can see on payments. Those induced stress are a function of the restriction. What do I mean? It goes between 0 and 1. So when we have no restriction, stress is 0, but when we have maximum restriction, when the concrete cannot move, the factor is 1, and this provides the maximum restriction. So induced stresses are proportional to specific deformations or potential deformations of concrete that may be or may not be restricted by something. In this case would be rubbing, for example, but these are inversely proportional to creep, for example. And if we have theoretical stresses and we have this kind of evolution, creeping would relax those stresses, and we could take advantage of this relaxing of the stresses. So if we have 100 or 200 meter concrete pavement, and after built we close the joints, we will see that there are some joints that work differently compared to the others. Some so-cut joints tend to open more than some others. And if we, after many months of years, we have this type of pavement, sometimes we don't realize, but if we have good measurement equipment, we can see that the pavement has this aspect, that's contraction and buckling. So basically, if we have a concrete slab, what are the effects of contractions? If we have a concrete slab, when dilation takes place, we have a shrinkage that is added to the superficial dryness, and then we may have also contraction because of cooling, because of the difference of temperature between day and night, and then there's some friction that tries to prevent that movement, and this generates tensile strengths, and cracks may be produced. So if we had a slab before, now we will have two slabs because there was a crack there in the middle, and this starts also happening in the divided slabs until it reaches an equilibrium, a balance. So this is very important. If we would not do any joints in the slab, the previous slab we had, after some hours or some days, we are going to have cracks. mainly because of that restriction. Why? Because if we have the same slab placed over a surface, we can see that at one of the ends we have no strength or tensile strength or stress because there's no deformations. As we go far away from the border, this starts increasing until it reaches its maximum point, and then between this distance and this distance there's a movement, so we have maximum stress. If the shear strength or the breaking stress of the material is over the induced stress, there's no cracking. As the induced stress generally exceeds the breaking stress of concrete, because the tensile strength is low, what we are going to have at a certain distance from the border a crossing, overlapping of stresses, as we can see here. So at a certain distance we have a crack or cracking, and once again we have a different diagram of stresses, and we can see stress going from here to here up to 0. And in crackings, there's no induced stress, basically. And if we see the intermediate point where we have the maximum stress, they never overlap. So there's no breakage in that point. So the objective of having joints is to place joints in places where naturally we will have crackings or close to those places. As I told you before, the restriction coefficient, which simulates these effects, goes from 0 to 1. So, which are the benefits of using recycled aggregate in a concrete pavement? Understanding that cracking depends on the retraction, the elastic modulus of the concrete, deformation and creeping. So, if we have some experience or several experiences in our country, but I'm going to focus on a paper presented over 15 years ago by 2 colleagues working with us in the company, and they studied the influence of replacing 100% of coarse aggregate with aggregates produced by the crushing of old concrete or recycled coarse aggregates. So they work with a reference concrete with granite addition and cement, and they compare that with 2 different aggregates produced by different recycling processes. They got some results that we don't need to detail now, but because it would not give us relevant information, but you are going to have the presentation available if you want to go deeper into it. So, as we can see some of the graphs, compression strength, we have in black the mixtures with 400 kilo cement, then and in green and blue the mixtures with lower content of cement. We can see tensile strength, static, elastic, dynamic, elastic modulus, and static elastic modulus. So we can see that there's a consistency here in the results. We can see that in the breakage modulus The mixtures in full line are those of the reference concrete, and the two dotted lines are recycled concretes. And so for the same cement content, we have lower tensile strength or lower strength when we have recycled aggregate. From the point of view of the compression strength, with the ultrasonic pulse speed, we can see that mixtures with natural aggregates follow correlation, and mixtures with recycled aggregates have a different correlation. And this is due to the fact that aggregates or recycled aggregates are a little bit more porous because they have some mortar. So there's a reduction in the ultrasonic pulse speed that is consistent with the density of those aggregates. So, but in contrast, is we use a sclerometer. These instruments does not distinguish recycled from non-recycled aggregates. So we are going to take advantage of these graph in the design of a concrete pavement. Why? Because the elastic modulus of a concrete shows quite clearly, shows very well the concrete, because concrete is a composite material, and it has an intermediate value between the coarse aggregate and the paste, the cement paste or mortar. So we can realize that if the elastic modulus of aggregate is changed, the concrete is also going to change, as well as this cementitious paste. So if our aggregates are the result of a concrete, as aggregates are recycled from concrete, we are going to have a lower elastic modulus in the resultant concrete. For at the same flexion strength, given the design of the mixtures for pavements, so at equivalent strength, we have a reduction between 19 and 27% based off the type of aggregates used. If we had to optimize the size of the slabs in the design of the concrete pavements, I mean separation between joints, if we understand that the induced stress depends on the degree of restriction, the elastic modulus, and the formation and creep, if we change the elastic modulus, we can modify the separation between the joints. We must not forget that a specific deformation has an impact on the separation between the joints, and this depends not just on the type of concrete we are designing, but also depends on, to a great extent, on the environment and the thermal expansion coefficient of concrete, which is also related to aggregate. So this is the first benefit we may have from the use of recycled aggregate. And this is, if we have a lower elastic modulus, we are going to reduce strength or stresses, and if the separation of the joints is related to an induced stress, we can increase separation between joints with having no impact on stresses or tensile strength. So if we do the math in a concrete example, if with a reference concrete we had a theoretical separation of 3.8 meter approximately. We can go to 4.20 with one of the aggregates or 4.67 with the other aggregate. So we have increase in the length or the separation between the slabs. So we are going to have between 10 to 20% reduction on the transverse joints. And of course, they have a cost, not just in the sawing of them, but in other procedures required. So another way of looking at the benefits of the use of recycled aggregate is that if we have a project such as these example that I did using OptiPave 2, which is quite common software used in the Pacific coast of Latin America, and given the same type of project, if we change the type of concrete used, is we include recycled aggregate that have a lower modulus, we can achieve a significant reduction in the results given by the software as regards the number of cracked slabs. So in 20 years for a project in the metropolitan area of Buenos Aires, if we use conventional aggregates, we will have 27% of cracked slabs. With one of the mixtures with recycled aggregates, we will have 20%, and with the other 17% of cracked slabs. So there's a clear benefit on the level of service and the life cycle of the pavement. So the other great benefit is that trend to cracking, or the degree or percentage of cracked slabs is reduced. Which are the benefits would recycled aggregates bring? In the specific case of the metropolitan area of Buenos Aires, coarse aggregates are brought from the center of the province of Buenos Aires. It's like 300 kilometers away from where we are going to work on the roads, and to be able to reduce the freight times and cost will bring about also sustainability benefits. It's not just savings of cost, but it's reducing the use of fuel, the CO2 production, and also would use also the concrete coming from demolitions, and also we have some benefits as to the disposal of those concrete. So conclusions will be that the use of recycled aggregates would enable us to increase the separation between joints because of the reduction of the elastic modulus. It would also enable us to have a reduction in cracking, and this would increase the level of service and the life cycle of concrete pavement, and we would also have sustainability benefits. So beyond the apparent benefits in terms of sustainability that are very well known, the use of recycled aggregates may also produce better solutions in certain projects compared to the use of natural aggregates. Of course, for this to happen, we will need to do certain studies and manage the project by competent professionals. And as a conclusion of my presentation, I would say that all over the world there's already many papers published on the partial replacement of natural aggregates with recycled aggregate, and this does not produce great changes in behavior of the concretes when used up to 10%. But this paper shows that the rational use of recycled aggregates, and we may even replace 100% of natural aggregates with recycled aggregates. So that's all for me, and I will be available for the Q&A session. Thank you very much.
Bueno, muchas gracias, Edgardo. Alejandro tuvo un inconveniente.
Thank you, Edgardo. Unfortunately, Alejandro, the next presenter, has had a technical problem, so I'm going to take over. And now we're going to move on to the next presentation by Thierry Sedran from France. Thierry is a civil engineer and he has a PhD in concrete mixes, and he has been working on cement materials and innovations for road applications for 20 years, and he's the head of the lab for structures and materials for transport applications. The title of his presentation is Recycling RAP in Concrete Roads.
Thank you. So I will present you some results about our modest experience in recycling RAP in concrete road in France. So in fact, in between 2001 and 2004, we did a PhD study in our department on recycling RAP into concrete, and this study was sponsored by the French Cement Association. And we did this study because at this moment, we had very few cases of recycling with hydraulic recycling RAP with hydraulic binder, and when it was done, it was always in well-graded treated materials and also in situ retreatment. So, and the situation was also that RAP was not as well recycled in asphalt material as now. So there was a real interest to try to diversify the outlets for RAP. That's why we started this study. Today, this interest remains for local needs to avoid, for example, movements of granular materials. When you have a stockpile and you don't know how to use it locally, you can use it for concrete. So we tried to introduce RAP into concrete because according to the previous experience in well-graded materials, it was known that introduction of RAP gives a drop of elastic modulus, which is interesting, as Edgardo explained just before. And we had only a small decrease of tensile splitting strengths. So the objectives of the study were to characterize the RAP, the influence of RAP on mechanical properties of concrete dealing with pavements, that is compressive strength, tensile splitting strength, elastic modulus, fatigue, cracking performances. And the idea was to find mathematical models which were able to describe the influence of the RAP on these properties, to introduce these mathematical models into the design pavement method, French pavement design method, to produce different scenarios to be able to optimize the use of RAP in different structures. So we focused on two types of concrete, one surface layer concrete with 330 kilograms per cubic meter of cement, and a lean concrete, a foundation layer concrete, with 220 kilograms per cubic meter. And for each type of concrete, we made five different ratio of RAP replacement from 0 to 90% of the total aggregate mass, total sand and coarse aggregate. The remaining 10% were due to the fact that we had to have a fine sand to correct, to change to optimize the granularity of the RAP. For each mix, we proceed compressive strengths, tensile splitting strengths, and elastic modulus tests at 28 days and at 3 different temperatures, 2 degrees, 20 degrees, and 40 degrees, because we used a bituminous product. And the results look like this. So here you have the trends for the 2 types of concrete. We will focus on 1 type of concrete, this one, the surface layer concrete. And you can see that when this is the compressive strength here, and MPa, and here the percentage of wrap replacement. You can see that when you introduce the wrap, the higher the content, the wrap content is, the lower the compressive strength as expected. What is interesting also to see is that when you increase the temperature, the decrease of the performance is higher also. This is because, of course, the wrap is becoming softer when you increase the temperature. We got the same trends for tensile strengths and also for elastic modulus. So with these results, we tried to develop models to predict these properties and the effect of the wrap. And finally, looking at our equation, traditional equation, we realized that we were able to account the wrap effect very simply by considering that wrap was introducing a bituminum volume in cement paste, and doing that, he was decreasing the performance of the paste. So, for example, for compressive strength, we know that the compressive strength is proportional to this ratio, to this formula, where we have the volume of cement divided by the sum of the volume of cement, the volume of water, and the volume of air entrained in the concrete with air entraining agent, multiplied by the coefficient. This coefficient was calibrated to be 0.5. Okay, so it means that a volume of air acts the same effect as half of the volume of the water. In fact, if you want to account for the wrap effect, you just have to change this equation and add a term, which is this one, where this term VB is the volume of bitumen coming with the wrap, and you have this coefficient beta prime, which is a coefficient which accounts for the effect of the bitumen. And this coefficient was found to be between 0.6 to 1.8. And the value, why we have different value, it's because of the difference of temperature. When the temperature is increasing, this beta value is increasing. It means that the effect of the volume of the bitumen is increasing. It means that this term is lower. It means that the compressive strength is lower. So with this simple parameter, we are able to describe the fact that introducing wrap decreases the compressive strength, and increasing the temperature will decrease more the compressive strength. And we have the same type of models for elastic modulus and splitting tensile strengths. As a second step, we did fatigue tests, and on the surface concrete with 3 replacement ratio between 0, 50, and 90%. And we did the same on the lean concrete, but only with 2% of wrap. With this kind of tests, we got the sigma 6, which is the stress leading to the failure at 1 million cycles. And you may know that from this value, sigma 6, we are able to calculate the maximum flexural stress that we can have in our pavement layer for a given traffic, which is here described by N. N is the number of heavy trucks the pavement will have to support during its life duration. These terms are classical terms described by our French design method. So this value will give you the fatigue resistance of the pavement. The results are the following. If you look at the blue columns here, the three first are the results for the surface layer with high content of cement and with different amount of wrap, 0, 50, and 90%. And you can see that the sigma cis value in blue here is decreasing. We can calculate the endurance. Endurance is only sigma cis divided by sigma 0, which is the static flexural strength. And you can see that the endurance in red here is also decreasing. So it means that sigma cis is decreasing because sigma 0 is decreasing, the tensile strength is decreasing, but also the endurance is decreasing. So this is a bad news because if the sigma cis is decreasing, it means that you have to have a thicker layer of concrete. So it's bad news for design. But we have also a good news. It means, which is the fact that when we make our fatigue test, we proceed several tests and we calculate a standard deviation, which is accounted for into the design procedure. Of course, if you have a big standard deviation, you have to take a large security coefficient in your calculation, and if this deviation decreases, you can afford a lower security coefficient. So the good news is that you can divide by 2 the standard deviation because of the introduction of the wrap. As a third step, we try to evaluate the crack tendency of the concrete, including wrap. As Edgardo explained just before, it's very complicated to evaluate this the crack tendency because it depends on thermal and hydric shrinkage level. It depends on the long-term elastic modulus or concrete relaxation, we can say. It also depends on the tensile strength of concrete. So the effect of wrap is very difficult to predict. We have positive effects because it decreases the elastic modulus, but we also can expect to have a viscoelastic behavior of the concrete due to the bitumen introduction. But we have also negative effect because we have higher shrinkage and also lower tensile strength. So to avoid very complicated calculation, we decided to use a restrained shrinkage bench to compare 2 sections of CRCP, continuous reinforced concrete pavement. So you have here the bench. The bench is composed with 2 high performance concrete, very stiff beams connected with steel beams. And here you have the 2 sections of CRCP, one with plain concrete and one with wrap. And the idea to simulate the shrinkage is to we have a kind of heat system in these beams, and we heat the beams to have the same. So you enlarge the bench, and it simulates the shrinkage, restrained shrinkage of the 2 beams here. So you have a picture here of the system. You have the 2 beams isolated, and you have the 2 beams without wrap and with wrap. They are not connected together. They are separated. And we compare two beams, beams with plain concrete and a beam with 50% of wrap. And in 2 cases with the same bearing capacity. In the first case, we had the same cement content, but we increased the thickness of the concrete with wrap. And in the second case, we have the same thickness, but we increase the cement content of the concrete with wrap to get the same compressive strength. And in both cases, we observe the same crack tendency with plain concrete and concrete with wrap. It means that wrap has no influence on the crack tendency of concrete, unfortunately. Then, with all this information, we made a theoretical pavement design we inserted the properties of the concrete into the French design method to calculate different structures having the same service life duration. So we studied this kind of structure with a lean concrete and a surface layer concrete. And for the traffic, we selected a heavy traffic TC5. We obtained this structure. We calculated the same structure with the same life duration with 50% of wrap into the lean concrete and the surface concrete. In the first case, we just adjust the thickness of the surface layer to get the same bearing capacity, and in the second case, we increase the cement content to get the same property as the plain concrete. And you can see in our calculation at this moment, we made the assumption that the cost wrap was €0 because it was considered as a waste. And you can see here that it was we can have solutions which were reasonable on the economical point of view. Please don't keep in mind this absolute value because this calculation was done with all the values, but we are able to calculate with real value now, and you depending on the local condition, you can make your own calculation. But I want you to retain that economically it's reasonable to introduce wrap into concrete, even if the concrete properties are decreased. We then did two real site experiments. One in 2003. It was in a rest area on the highway in the southeast part of southeast of Paris. And we first mill the bituminous product on this area. We milled the wrap, and the wrap were recycled in a 10 centimeter wide cupping at a percentage of replacement of 40% of total aggregate. And we poured the concrete without doing any joints because we wanted to see if we had a better crack tendency. And of course, as explained just before, we obtained that we had the same crack tendency without a joint, but we had a very good behavior of the overall behavior of the structure. The second one was done in 2009, and it was made on the main road in a business area in the northwest part of Paris. And in that case, it was independent concrete slabs. And we had a pavement of 800 meters, which was separated in three sections. The first section was made with plain concrete with 18 centimeter thick slabs. The second section was exactly the same, but we introduced 40% of wrap into the concrete. So we get a lower tensile strength, 2.5 MPa, but it was still higher than the minimum required by the design, which was 2 MPa. And the second section was exactly the same, but we introduced wrap, 40%, and the slabs were 22 centimeter thick. And you have two pictures of the experiment, and the three sections behave very well up to now on the traffic, bus traffic mainly. And also what is interesting is that the photometric measurement we did here confirm that although wrap are dark, they do not affect negatively the reflection of light by the concrete surface, which is very important for the lighting management in urban area. This is a very important point. As conclusion, we have models to predict the properties of concrete, including wrap, depending on the temperature and the proportion of wrap. And we can use these models in collaboration with the pavement French design method. The effect of the wrap are accounted through a very simple parameter, which is the volume of bitumen brought into the paste of concrete. And from a pavement design point, replacement of natural aggregate by wrap has a negative effect by lowering the tensile strength and fatigue endurance of concrete. It has a positive effect by lowering the elastic modulus and so decreasing the tensile strength in the concrete, and also by decreasing the dispersion on the fatigue dispersion of the fatigue test. And it has no effect on the risk of cracking, unfortunately. Finally, the recycling of RAP into pavement concrete does not raise technical problem. The decrease in service life of concrete pavement, including RAP, can be compensated by an extra thickness of concrete layer or an increase in the cement content. And calculations show that these two solutions may be economically viable and must be of environmental interest when unused RAP stocks are available near a construction site by avoiding transportation of natural aggregate. Thank you for your attention.
Thank you, Thierry, for your excellent presentation. En este momento vamos a dar lugar.
Now we have our Q&A session, and I will read the questions that we have received during the presentations. Let's open the session. The first question is for Edgardo, and it's by Rafael González, José Rafael González. And the question is, which are the minimum and maximum separation, the minimum and maximum recommended separations between slabs? Between joints, sorry.
Sí, Edgardo, te escuchamos bien.
Bueno, gracias por la pregunta, Rafa.
Thank you very much, Rafael, for the question. In fact, joint separation is related with the environmental conditions and the characteristics of the concrete. We are used to having recommendations of 21, 24 times the thickness, but that's rules, practical rules that can be taken as a reference to make some tests during the project evaluation or assessment, but the actual separation between the joints would be on a case-by-case basis, and it's part of the job of the design engineer to adjust this number. What I say that if we use recycled aggregates, given the lower elastic modular, if the thermal expansion coefficient is the same, because the aggregate used in the area will be the same type of aggregate use if natural. So the thermal expansion coefficient is similar, though the recycled aggregate has a little bit higher coefficient because of the reduction of the elastic module. We can increase but 10 to 20% the separation between joints without increasing the strength or stresses. Thank you very much. I have another question for Edgardo, or at least two questions made by Darío Figueroa. The question is, which is the maximum strength obtained, and do you know different costs, the difference in cost between natural and recycled aggregates? In fact, we have not done study just to check up to what extent we can increase strength or tensile strength, but given the strength that we use for pavements, which is 45 to 50 megapascals, the values are quite similar. There's no significant reduction in compression strength when we use recycled aggregates. The difference sometimes is observed in flexion and tensile strength, but In the examples I showed, mixtures were adjusted to the same flexion strength. And that was the first question. The second question, as regards costs, depends on each case, but in the case of the metropolitan area of Buenos Aires, we have significant savings because we are saying that we are saving 350 kilometers of freight cost, but the crushing process also implies cost. You need to have a mobile plant and you need to study it on a case-by-case basis, but it's going to be cheaper, but we don't know how much cheaper it would be. Another question for Edgardo by Gustavo Berretta. Gustavo's question is, how do you control the percentage of humidity in the different aggregates, and what's the maximum strength you have obtained, similar to a previous question, and what happens with water cement ratio? The recycled aggregate is worked exactly the same as a conventional aggregate. From the point of view of checks and controls, they are exactly the same, and there's no difference in the determination of humidity. And the water cement ratio, if we do dosage control, it's similar to the conventional aggregate, but I did not include some things in my presentation, but I showed there that there were some adjustments in the water cement ratio in order to obtain the same flexion strength. In the reference case, we had 300 kilos of cement, and in the recycled cases, we had 330 and 340 kilos of cement. So there was some changes in the water cement ratio in order to have the same results. One last question for Edgardo by Roberto. And can you tell us the reason why we have plain concrete pavements with over 50 years of service, with joints separated by 50 meters, with a percentage of crushed slabs, with cracking? And maybe that the aggregates had lower quality at the time, or different behavior, or that concrete had better granular structure and require lower amounts of pool and cement to achieve the required behavior. I don't have a clear answer, but what I can say is that I've seen many pavements in the province of Buenos Aires that are 80 years old and are perfect, are in perfect condition. But I also know that in many of them there were no traffic, or they are low traffic volume roads. But I come from Loma Negra, the town of Loma Negra in the province of Buenos Aires, and the main avenue in the town is made of concrete. It has exactly the characteristics mentioned in the question, and so it's perfect. It has a perfect condition, and all the trucks coming to the factory up to the 70s had to go through that avenue, so up to the 70s. So I have no all the trucks that were to the quarry manufacturer went through there, and the condition is perfectly good. I have a question for
and Edgardo, and which is your vision in the future for the use of RAP in concrete pavements. If you want, Gina, you can start and share your vision.
Thank you. We've had a couple of states or agencies within the United States try wrap in concrete. And we've found it's most economical when there are areas with large wrap stockpiles. And so it's not the right decision everywhere because of cost and sustainability trade-offs. But in some instances, it is a very good decision. So we really do recommend a lot of trial batches and sections to see if, what concrete mixture the agency is using to make the wrap work within that mixture.
Perfect. Thank you, Gina. Thierry, could you?
I share the vision, Gina's vision. In fact, of course, now you know that wrap, it's more logical to use wrap into bituminous product because you have a real synergy between the residual bitumen and the new bitumen. When you introduce wrap into concrete, there is no synergy. You just have to face decrease of performance. But it can be a good solution when you have a big stockpile, which is local, and you don't know how to use it in a bituminous product because perhaps your wrap is not of good quality, and you know that concrete is less, let's say, it can afford bad product more than bituminous product because of the cementitious reaction. So we can afford to have lower value wrap. So it can be very interesting if you have a big stockpile, and it was the case in my second example. It was the case we had a big stockpile, and nobody wanted this stockpile because it was not of good quality for a bituminous product. So we use it because it was very near from the site. We use it to produce this concrete. So we save a lot of money due to natural material transportation. So you have to make. That's why it's interesting to have this the model we have is because you are able to evaluate the maximum or the optimum wrap content you have to have in your concrete, and the cement you have to use to face or to face the decrease of compressive strength, for example. And of course you have another cost with the cement, but you have a lower cost due to the wrap replacement, and you have to make your economical calculation and environmental calculation. So as it is true in general for environmental solution, you have to make your local calculation. What is true in a site won't be true in another site. That's my point of view. So it's not a general solution. I don't think it will be generalized, but it's a good solution for local problem.
Clear.
And we have all the tools.
Yeah. Thank you, Thierry. Edgardo, tu visión.
Your opinion, Edgardo, on the issue? I agree with the fact. The only thing I should clarify here that in my presentation, I talked about concrete recycled, which is recycled concrete, which is different from wrap. But my opinion is that the use of recycled materials for new construction works is a need, is a requirement. So we need to adapt to the situation. For example, in my presentation, in the case of concrete recycled or the use of concrete recycled concrete aggregates has an economic advantage and a technical advantage. In the case of wrap, I think that is more oriented to the need for using recycled materials, and not just necessarily because it's a better product. So thank you very much. Thank you, Edgardo.
The presentation. Y de esta manera,
And with this, we close the first session of this third day of seminar. And so after the break, we have some minutes break, and then you can join back to share the last session of this day. Thank you, everybody. Thank you to the presenters and the audience. And we wait you back in some minutes. Thank you very much.
Good morning, everyone. We are starting the last part of our PIARC seminar on the use of recycled materials for pavements. And it's a very interesting day because we left for last the analysis of recycling techniques for asphalt material in hot, warm, and cold mixes. That is to say, we have the whole range of uses for this valuable material, which is so important for sustainability of pavements. The first presentation is about how to recycle non-conventional mixes with non-conventional materials by Jair and Damián Giménez. We all know very well who Jair is, especially as the manager of Shell and author of 2 of the Shell Bitumen Handbook. And Damián Giménez is the head of the research lab in a company which has 25 years of experience, and the chamber dealing with conventional and unconventional materials. They have 20 minutes for their presentation, so Mario, Damián, you have the floor. Hello, everyone. Good afternoon, good evening for some of you. It's a pleasure to be here and to share this seminar with our distinguished colleagues. Thank you, Pablo, for that introduction. And first of all, the idea for this presentation is to make an introduction and talk about recycling in Argentina.
Reciclado de todo tipo, de hormigón, de cemento, en plan.
We are going to deal with recycling of concrete in different mixes, even with incorporation of rubber and waste of all kinds. So we're going to talk about the situation of this recycling in Argentina. Then we're going to talk about different types of mixes, design mixes with RAP and reuse in special mixes. We are not going to talk about recycling, but rather reuse or reclaiming and evaluation of materials for those designs. We are going to talk about the characterization of modified RIP coming from mixes that already included RAP, which has been used in Argentina since 1996, the characterization of virgin bonds, then design of mixes with compaction according to granulometry, volumetric dosage, and finally WTT and HWTT. Finally, we are going to come to some conclusions that we hope are going to be useful. The main idea of sustainable solutions can be summarized in this graph that shows circular economy, which means reusing and leveraging the elements that we have, and this is cross-functional to all of the industries, and particularly it involves pavements. What is new regarding RAP? For example, Europe yesterday showed us, and I have to say that I'm quite envious of what they do in Norway with RAP, which should be a model for management and usage of RAP for the authorities. In the industry of asphalt pavement, we need to foresee what we're going to do so as to generate a minimum of waste, and from that we have the long-term or long-duration pavements. I prefer not to use the terminology calling them perpetual or perennial. If there's no prevention and there is deterioration, we should try and minimize deterioration, and we start working on preventive conservation. If we go to reuse or reclaiming materials, then we start thinking about mixes, reusing materials, mixes with RAP, with special surface layers that is going to go back and be reused for new mixes. And if there's no alternative, then we are going to recycle, and those materials could be used for other uses. For example, the subraise or reconfiguration of shoulders. But this is the whole picture when we talk about recovery of high value materials. And finally, there could be recovery of energy, and if there's no alternative, dump as little waste as possible in the right places. Recycling in the asphalt industry or in our industry is something that started in 1955 with the use of RAP. Usually it was combined with oils to do in situ mixes, and then in 73 with the oil crisis we started to do recycling of mixes with asphalt. Then we started talking with soils, granular materials, concrete. Gina gave us a great presentation this morning about the reuse of plastic too. And the reasons is because of restriction in costs, because of the restrictions towards virgin material, and the legislation, which is more and more restrictive regarding the compliance with environmental laws and standards. The goal is to reuse, and I think this is something that Curro is going to say, to start talking about reclaiming or reuse. The trend is to have more conservative ratios, like 30%, but mass use. That is to say, use as much RAP as we can, but in combinations that are conservative at around 30%, although there are some cases where we do 100% reuse or 100% incorporation in mixes. When we talk about in place, in Argentina, this is a situation that is rather new, and we're starting with experimental stretches. You know that the on-site recycling in hot mixes is normally done for overlay in narrow layers, about 5 centimeters. If we talk about emulsion recycling, we have a great experience in Argentina, which started in 1998 and took up until 2003, but this was not leveraged properly, because even though there are very good emulsion suppliers, this was discontinued. And I'm proposing here something that we've said many things. This should be revisited. When we talk about foamed mixes, this is something that we've seen in Uruguay, Chile, and Argentina. We're starting doing tests and with some works like engineer Pablo Morano showed yesterday in the province of Buenos Aires. Regarding hot mixes, in-plant hot mixes, for recycling, we've been doing this with RAP for several years regularly, but there was no standard to use as a guideline. And since 2017, there were new regulations adding the use of dense mixes, hot or warm, dense mixes with RAP. It is important to clarify that this standard applies only to dense mixes, but with RAP with conventional mixes. If it is less than 10% of RAP, there's no consideration, so that's like a tacit invitation to use up to 10% of RAP in any kind of mixes. And then the guideline applies to combinations with a percentage of RAP that goes from 10 to 50%. And then we have new challenges. As we said, reuse of RAP in special asphalt mixes. As we saw yesterday, one example of high modulus mixes with RAP as the raw material. Then the use of modified RAP, especially when it comes from asphalt mixes that were done with special binders and with aggregates that were special quality. So it's a very good reason to reuse them. And finally, WAM in warm mixes, it's called WAM wrap. This is the future of the options that are part of our industry's agenda. And that is what we're going to refer to today. Special mixes with special or modified RAP with the possibility of using it in warm mixes. Regarding the design mixes, this is something that started many years ago and was presented in different congresses, for example in Obitun in June this year. What we're going to show is the design of a mix that is called MAC F10. I'm sorry I'm using an old classification nomenclature, but this is what appears in our legislation and standards. Then we refer to discontinuous hot mixes or thin overlays, and here we're referring to BBTM if we were talking about Spain or France. Those are called MAC F10 in Argentina. If there's an R, it means that there's a percentage of recycling, and after that we have the virgin bind that we use in the mixes. We have two MAC F10R mixes with a contribution of RAP or RAP that was produced in 2001. This is a mix that is 20 years old at 20%. That's what we call MAC F10R20. That means 20% of this RAP. And we use MA3 as the modified binder that is mostly used in Argentina. And then there's another one, mix called SMA19AM3 that was used in 2005. We are using two mixes that are 20 years and 10 years old that were using modify RAP at 20% and 44% respectively. We are going to also show you a design with a variant using low temperature binder, that is to say a warm variant, to show the benefits of both technologies. This is what we call WAM wrap. If we evaluate the materials, We see granulometry here for RAP in the two mixes that I'm referring to, the one from 2001 and the one from 2005. We had two fractions, a coarse fraction and a fine fraction, and we are going to see the characteristics of the recovered binder.
Recuperado de la mezcla del 2001.
This is the one with the characteristics from recovery materials from 2001 and 2005. And here we can see the excellent behavior, despite they are 15 and 20 years old, of the binders used in the mixes, which maintained elasticity, especially elasticity regarding torsion. And something else that was verified is that viscosity of these binders after 20 years have practically maintained the original values. So, as we have said, viscosity is not a factor that can help us in measuring the aging of these binders. These are the binders that we used. On the left, we have AM3 for binders that were modified in Argentina. The type AM3, and that's the most popular binder used in Argentina, with minimum time and penetration of 65. We are thinking about using MMCCR in the future. And next, you can see AM3LT characteristics. It's AM3, of course, but this is low temperature. So that enables you to use lower compaction or lower shrinking temperatures. There you can see comparative dosage for the MAC F10 as reference with virgin materials, with two arids plus a filler, as stated in our regulations. And you can see that the use of 20% of RAP for both types of binders limits the utilization of 0.3, and if we lower the values in aggregates, it incorporates 20% of RAP, which contributes 20% of binder and contribution of 4.1 of virgin materials. When we talk about SMA at 19 millimeters, you can see that 44% is divided between 68 of fines and 32% of coarses, and we have eliminated 0.3. We have eliminated one of the virgin arid fractions totally, thanks to the contribution of RAP. If we look at MAC F10 R20, on the left you can see the use of virgin materials, and on the right you can see incorporation of 20% of RAP. Both of them are within the values of the regulations, and there are no problems with granulometry or discontinuity of granulometry. Here, with 44% of the SMA mix at 19 millimeters, you can see that there were no problems. So we have volumetric dosing because of the Marshall testing with RTI. And you can see here that the compacting temperature in all of the cases is 160 degrees, except for the warm asphalt, where we worked at 120 degrees. And in that case, we're using warm binders. So as you can see, the content of the binder in the mix have been reasonable. And in the last two lines, you can see resistance or tensile strength and resistance to damage by moisture that we can have in the Argentinian experience. If we talk about mechanical performance following the Argentinian standards, we can see the values of the reference mix, in this case in blue, and the MAC F10 with M3 as the binder, and we can see that we are within range for rotting depth, for example. And here we have the AM3 for low temperature in red, and even though we can adjust some of the values, we are within range in the rotting standards, and so there's low rotting because the whole overlay is 3 centimeters, for example, so the aggregates themselves do not allow for a lot of rotting. Here we have a mix with a contribution of 44% of this asphalt mix, and there's better behavior or more stiffness thanks to the higher percent of RAP in the mix. Additionally, in the case of R44, we did a lumber test where we don't see a difference in the curve because of changes in moisture on the surface. So this shows that mixes are compliant with the mechanical specifications. The conclusions say that we had 2 mixes, MAC F10R, one with 20% of RAP, which is 20 years old, and the other one with 44% of RAP from 2005 with an SMA that is maximum 19 in size. I don't know. I don't know. Okay, there we go. The good thing is that I am here in the same room, so they can help me with the technical issues. We also designed a variant of MAC F10 R20 with a warm AM3, and both the volumetric performances and mechanic performance enables us to anticipate a behavior that is similar to MAC F10 AM3 with virgin materials, which is something that should be confirmed in an experimentation or a test that we're going to do. We were going to do it this week, but we were not on time for that. But we are going to have very soon the data from this test, and we're going to include it in the presentation so that you can check that. Of course, it is very important to highlight the reclaiming and reuse of RAP from aging mixes based on modified asphalt for new rolling surfaces with the same features. RAP is high value, but when it comes with mixes with special binders that we're already demanding in terms of quality, this is a material that we want to reclaim and reuse. And in any warm LT mix for the WAM wrap mixes, this is available in Argentina, and it could provide a synergy between both technologies, and this is what we saw in 2017 with the new technologies and the incorporation of RAP on the one hand and warm mixes on the other hand. Thank you very much, and we're looking forward to your questions.
Thank you, Mario. You have an fine in euros because you have go over 4 minutes in your presentation, but okay, you are forgiven. So let's go to the next presentation, which is the half-warm asphalt mixture with emulsions, and this is going to be presented by Francisco. José, he's the Director of Asphalt Business Units in Repsol, and he's vice president of another company in the sector.
Te falta el sonido, Francisco.
You are muted, Francisco.
No.
Bien.
Ahora
Ahora se me escucha mejor.
So, can you hear me now? Yeah. So, thank you for the introduction. So, first of all, I would like to say hello to all the attendants to this seminar, and of course, thank the Argentine Road Association for the great organization. Today, I'm here representing the National Spanish Committee by the National Road Association of Spain. As Mario Jair said, I'm going to talk about warm recycled mixtures with emulsion by sharing with you the example of one highway in our country. So my presentation first would do a presentation of the different types of bitumen mixtures in terms of the manufacturing temperature, so that all of us are on the same page. Then the design objectives of what we call emulsion warm mixtures, and the reduction of temperatures in bituminous mixtures may be an opportunity for the for taking full advantage of RAP. And I would like to talk about the spread of new binders in old binders in reuse techniques, and I will share a case study in one of the Spanish highways. I think that all of you already know this graph, at least all of us specialists in asphalts, and this it's a graph on manufacturing temperatures and the fuel consumption based on the temperature. We have consumption and temperatures, and you can see the differences between hot, warm, or half warm or cold mixes. Over the last years, more than we may think about it, we saw the emergence of half warm techniques, and these over that value of 100 degrees about the evaporation of water, and below 100 is the ones called half warm mixes and anaerobie semi-tièdes in French. And so these are the ones I'm going to talk about during my presentations. So, and we ask why? Why to design half warm mixes when we already have cold and hot mixes? So if we think about the advantages or characteristics of each of these techniques, we know that emulsions in cold mixes is a product that can be managed at ambient temperature, and that cold mixes have low environmental footprint, and that hot mixes have been considered because they had good mechanical behavior, and of course at low cost, without thinking about modified bitumen that have a great behavior facing deformation behaviors. So if we consider hot mixes, they contribute with good modulus, enable designs that can be used with heavy traffic, and also the hot mixes enable the use of viscous binders. And if we combine these three concepts related to the performance of bituminous mixtures, rigidity, stiffness, and we introduced an additional item such as the abundance of hot mix plants, and we try to look for an optimal solution, we may have that concept of half-warm mixes that is just the result of trying to combine the qualities of both cold mixes and hot mixes. So, at the beginning, we had a graph with the type of mixes based on temperature. We could do the same with the recycling concept, that it would be better called reuse based on the manufacturing temperature we may have. One of these 4 stages: hot recycling, half-warm, warm recycling, half-warm recycling, and cold recycling. Historically, cold recycling has been done in place, and the other 3, hot, warm, and half-warm, are normally done in plant. As regards the recycling rate or the RAP rate incorporated in the mixture, the problem is that the equations we need to consider to rule this thermodynamic system balances the ones you have there. So we can go from the liquid state to gas state due to the presence of water in the mixture through emulsion. And which are these 3 systems? It's quite clear. First, we have virgin arid, the new binder, to add that, and the temperature will be conditioned by the viscosity, and the material to be reused, that we call generically RAP. And if our mixture has high manufacturing temperature, the RAP to be used should have a lower mass, because RAP typically is introduced at ambient temperature into the system, regardless of the fact that we may modify some manufacturing process. But in principle, it's a simple question of equations that need to have the same equivalent value. If we go to our next slide, as heat transfer, in principle, is quite simple. The spread of the low binder, of the old binder into the new binder, is not so simple as it may seem. At the beginning, as Jair said, as regards viscosity, in Europe we defined the consistency of bitumen at high temperature and at service temperature through penetration and softening point. And it's not just to mix the old and the new bitumen until we have the right combination, because we all know that when bitumen ages, its composition also changes, and the ratio between composition and properties can be explained through the SARA concept: saturated, asphaltants, aromatics. And so the composition of the RAP will be more similar to what you can see on the upper picture, and when it's aged, you would see a structure much more similar to the one that you have at the bottom, like a gel structure. And for relevant RAP rates, these cannot be overlooked. We would need to add additives to restore the composition, and these are the ones we call regenerating or rejuvenating agents. And this is an aspect very important aspects to have into account. As I told you before, I'm going to present here a case study of rehabilitation of a service road, the A1 highway in Burgos, and this rehabilitation was the result of the new program of the Transport Ministry to rehabilitate all first generation highways. We took a 1,300 meters stretch that was divided into two. One had 2.5% emulsion, and the other.
¿Es posible que ahora sí que lo vean? Correcto. Vuelvo a pedir disculpas.
Okay, sorry. Today technology is not on my side. So, as I was telling before, here we have the rehabilitation and the manufacturing of a half-wall mixed with 5 centimeter layer with a technology similar to what we call here asphalt concrete. It's a continuous mixture with a wrap recycling rate of 5%. So we have T2 traffic, intermediate traffic over this road, and the contractor was Sasir, and the emulsion was manufactured by Repsol. So something quite complex, such as the manufacturing of this type of mixture for such a high important traffic volume in a highway, required many studies that could not be just described here in some minutes. So I have chosen some of the most relevant aspects of this process. So in a mixture where 100% is made of wrap, what the authors call milled material called MFMB. So here the protagonist is wrap. And so the first issue they have to face is the determination of the granulometric curves to be consistent with the continuity required and demanded by asphalt for intermediate layer. So, in my opinion, they really complied with the Spanish regulation of cold mixtures, and from there they started doing the first dosing, as you can see on the graph to the left. And so the softening point of that material was way over the allowed value. They realized that when this material would heat, it would soften, and so they went to the granulometric curve of AC16. They removed the binder, the residual bitumen binder. It was removed from the milling product, and they just did the reverse process. So in the end, the composition of that wrap would be at 40% from 0 to 5 millimeters, and 60% from 5 to 25 millimeters. As to the reclaimed binder, they recovered 4.85, and the 0.5, the finest fraction, had more like binder than the coarser fraction that had just 1/3 of the fine 2.47. As to the quality of the binder, there was heterogeneity there, but you can see the mean values obtained by the finer and the coarser fractions. You could see that there was a ring and ball higher on the second day compared to the first day. For example, up to the manufacturing of the mixture, here we have the core of the question. The fractioned wrap is introduced to control the regularity of the mixture. You could see the two conveyor belts there. And heating should not be aggressive in the case of wrap, given the fine fraction. So if we heat it below 100 degrees, we will damage the residual binder contained in the wrap. So for that, a new and innovative system was created with a parallel flow drying drum, where the coarser fractions that required more time to heat would be introduced first, and the finer fractions would be introduced later at the end of the parallel flow drying drum. And the truth is that at no point in time the flame would be in contact with the milling product with the wrap, but it would heat the gases derived from that combustion. And they even thought about a recirculation system to take the fullest advantage of the whole system. So this system that you can see there on the slide, it was an independent standalone system that can be coupled to a conventional discontinued or continued plant. So it can be adapted easily to any type of hot mix conventional plant. So results from the point of view of cohesion were very good. You can see there the data of the preserved consistency with the different emulsion percentages, 2.5 and 3, and results were better in one case compared to the other, but in both cases they were powerful and reasonable to be considered for use in the layer that was being manufactured at the time. So when we think about mixtures manufactured with the use of emulsion, we always think about curing because certain hydraulic binder have to be incorporated in the system. But this is far from the reality in this case, because the manufacturing temperature here is close to 100 degrees. So for the beginning of the manufacturing, water is evaporated, and then you can see that at 19 hours everything is cohesive and the consistency is preserved over 90%. So here you can see the works. You have pictures of the thermal camera, the laying of the lay, and Burgos is not a warm area, a warm region in Spain, but the reduction of temperature is reasonable and the loss of temperature during transport is not so high, though the plant was quite near the working site. Just 2 or 3 degrees were lost during the transport of the mix. And then you can see compacting with compacting elements. And of course, all of us are concerned when we have wrap and the mixtures that compacting conditions should be different or strange, or that we may have holes or empty holes. but here we have no issue whatsoever, and compacting was properly done. We were able to obtain reasonably good modulus between 3,500 and 5,000 megapascals. So conclusions is that reduction of manufacturing temperature enables to develop new reuse techniques for bituminous materials. The half-warm mixtures enable the use of rate up to 100 wraps, optimizing the service of these hot and cold mixtures. And recycled mixtures, half-warm recycled mixtures with emulsion are feasible from the technical and economical point of view, and I would not like these to turn into a competition. The higher the recycling rate, the more favorable would it be from the environmental and sustainable point of view. But I always say that we need to calculate the carbon footprints in a case-by-case basis, and also to see whether we have availability of the reclaimed material of the milling material, considering sustainability in each case. And I hope that I have not run out of time, and I would like to thank the National Road Association from the Transport Ministry in Spain, because they have allowed us to test and develop this technique in one of the highways. Also, I would like to thank Jair for providing all the information required to make this presentation. I also would like to thank ATEB, the Bituminous Mixtures Institution, promoting the use of bituminous mixtures, and finally Engineer Jacinto Luis Garcia Santiago, who's being a good promoter of these techniques, and he has helped me to make this presentation, and he has contributed a lot to the development of this technique. So once again, I would like to thank PIARC for the opportunity to make my presentation here, and there you have my Twitter account, and I will be available for the Q&A session. Thank you very much.
Bien, muchas gracias.
Thank you very much, Curro Lucas. Can you see me on screen?
¿Estamos en pantalla ya?
Can you see me? Am I on? Okay. Thank you for that presentation. And we are going to continue with cold recycling now, with emulsion and asphalt recycling agents. This presentation is by Luis Gutierrez Klinsky, evaluator of projects from CAF. So from Brazil, he's going to give this presentation about cold recycled asphalt mixtures. Thank you, Pablo. Good morning, everyone. My name is Luis Gutierrez. As Pablo said, I'm working at the CAF in Latin America and in the work group 4.1 of PIARC. So first of all, I would like to thank PIARC and the Argentine Road Administration, and I'm going to tell you about my experience in cold mixtures for recycling of mixes based on the work of Engineer Munger in Sao Paulo and Rosangela Mora. In Brazil, we've had a good experience with reclaiming and recycling of pavements, and specifically in the last few years, we have prioritized cold recycling because of the different advantages that it has, and because it is easy to adapt for companies to use this technique. Many of these applications have been incorporated in federal projects, and some of them have been executed by private partners. especially taking into account that the road network in Brazil is very extensive. Today I'm going to talk about a road in the mainland São Paulo using 100% of RAP with heavy materials, and we prioritize the use of an asphalt emulsion to be able to leverage most of the material that was available, the stockpile. We are going to show you, I'm going to show you lab data in this experimental stretch, which is 4 or 5 kilometers, and the results that we've had in 1 year of use. When we talk about cold recycling, as you've seen in these 3 days, we can use different materials, but in this specific case, we chose to work with an emulsive asphalt mix with recycling additives. We know that these can be vegetable or mineral to promote workability of the mixes and also to deal with the mechanical characteristics that we need to obtain for a certain project. Thus, we can classify this in these 2 big groups according to this special emulsion stabilization, where we can have cold stabilized recycled mixes with inactive asphalt, and here the behavior is hybrid between a granular mix and an asphalt mix. And on the other hand, we have when we have a good percentage of active asphalt, we have these recycled asphalt mixes that tend to behave as asphalt concrete, although we don't get that far when we do hot production. And then in these asphalt mixes, we have higher dispersion, as we've seen in other presentations. In this case, the asphalt emulsion shows more dispersion of residual asphalt, in part due to the use of recycling additives, but also because of the thickness of the film, which is considerably lower than we would have in a conventional hot asphalt mix. For the specific case that I'm going to present here, we recycled approximately 10,000 tons in an area in the interior of São Paulo. We followed the recommendations in RILEM 2015 archives and also following ARRA regarding the standards for granulometry, where the requirement was to have medium granulometry. We also did recovery of the asphalt binder using the Abson method, and we had variables of up to 4.3 in this milled material. Also, we had rust in the layer, and there was rotting, or the softening point was at around 92 to 95 degrees centigrade. The option here was to use a special asphalt emulsion modified mix. It was modified with SBS. It was a cationic mix with slow rupture, and the company that conducted the formulation for this emulsion also collected milling material where they analyzed the rusting and specific surface of the layer. We followed AARRA CR 201. We used a Marshall impact test with 75 impacts per side, and we also used the procedure at 40 degrees during 24 hours, and according to the manual, we applied two criteria that were defined for ideal content, which could be Marshall stability, which was chosen in this case, and due to several combinations and depending on the water content, we got to the ideal percentage of 2.5 regarding water content. We used RT 500 when we talk about in plant. This could be used in place, but in this case we used a fixed configuration to do in plant with a TMN of 31 millimeters, deaggregating the material, and there was also a double axle mixer for the production of the asphalt mix for homogenization. Once we completed this process, the material was produced in volumes that were sufficient for the work, and I'm going to show you some of the results, telling you how long we could maintain this recycled mix in storage before it was used and compacted in place. This is a representative sample with these cores that we took to the lab to check shrinkage and the density and vacuum volumes. Here we used Marshall 50 impacts and 75 impacts, and gyration at 50 and 75 also. And we can see the lower densities with more vacuums, and 75 and 50 impacts gave more approximate values using Marshall shrinkage at 75 impacts. With these materials, then, we analyzed the storage time, that is the time between mix and compacting. We stored the material at room temperature that could vary between 20 to 30 degrees depending on the season, and it was stored for 7 days, 14 days, 28 days, and we also analyzed 56 days. In the case of the cores at more than 75 impacts, we see that after 1 day of curing, there was no resistance after 7 days and after 14 days, and even it could be beneficial. So during this storage time, there was some reaction between the residual RAP asphalt and the emulsion agent. After 3 days, we see an increase that is considerable, and 7, 28, 56 days, we see that the best results were in a storage time between 14 to 28 days. Here, for curing time higher than 7 days, we saw values over 300 MPAs, which is the value recommended by the manual from the American Association of Reclaimed Asphalt. The objective here for this course was to do stiffness tests doing cyclic diameter compression, and we used the Brazilian standard in this case, and we could see that the first day there were stiffness values in the probes or the cores. After 7, 14, and 28 days, in storage, and after that we started seeing constant values after 14 days and 28 days in storage, with values that are around 2,000 MPAs. At the same time as we were doing these lab tests, the works were underway, and these works had to do with one light traffic lane. Lane 1 was for fast traffic. This was projected at a useful life of 10 years, considering that this represents 3% of the total road traffic in this lane, and we had planned to have a conventional structure starting with the subbase, then a reinforcement, dry macadam, and then an overlay of asphalt of around 7.5 centimeters. So this project started with the base with a special asphalt emulsion, and also as the reinforcement for the sub-base we included this material, which is waste from civil works that was stored independently at the waste area in the company. We started then with this sub-raise of this broken material, and then we used the emulsion with a structural coefficient that is according to the ARRA manual, indicating values of 0.30 to 0.35 for this material. We use 15 centimeters, then an asphalt layer of 5 centimeters, and then micro pavement for traction criteria. Once the reinforcement was built with these materials from civil construction materials, we also built the sub-base with broken material, and for construction of the base recycled with the emulsion, we used the asphalt machine for pre-compacting, and for the intermediate final compacting we conducted several tests using combinations with kickstand machines, as you can see on the left, but in the end we used standard rollers that used a pneumatic roller. This 15 centimeters was done in two overlays. One was 10 centimeters or 8 centimeters, and this was dried up until we got to 3% moisture, and then we applied an asphalt emulsion for the application of the second layer of recycled material, which was 9 centimeters, in order to obtain 7 centimeters after compacting. We did shrinkage control following the conventional protocols set by the regulatory agency with the sand box that we see there. The recommendation is 5% with Marshall at 75 impacts. We got to 97% in 5% of the stretch. The rest was all about above 95%, and we used a geo gauge to measure stiffness as we made progress with shrinkage. Between the first layer and the second layer, we dried the material, or we allowed for drying time, and then we laid the second layer with the same procedure to finish off with the asphalt overlay. It was built the asphalt overlay was built 15 days later, and the whole process was done with conventional equipment that is commonly used in the region. We can see the recycled stretch. The recycled stretch was tested a year later using a deflectometer FWD. We see high reflections, but we obtained values that were constant between 180 and 360 days with zero deflection, with approximately 200 micro-m. We did retro calculations here to observe the stiffness of the modulus at 90, 180, and 360 days, which was constant at 1800 MPAs, that were very similar to what we obtained in the lab for cyclic diameter compression of the cores. We also conducted BDI, and we obtained values showing that the cure had taken place, indicating that there was a good reaction between residual RAP asphalt and the additives used in the asphalt emulsion. We also analyzed our IRI values, and we see here 1 point a little bit above 2, which is a value that normally is used as control of the good execution of the stretch. So we see that this needs to be improved. Sometimes the companies do not want to use different materials, but this can show progress as we work with this material. By conducting this control, we did transverse profiling, and we found that the values were under 4 millimeters after 500 days. There was also a control, or we checked temperatures and rainfall. When rainfall was around 400 millimeters per year, there was no, it did not affect the supporting capabilities of the asphalt. Regarding the environmental and cost aspects, this was a conventional solution. This substituted a conventional solution, which reduced the use of new materials and reduce of dumping areas. The asphalt mix meant savings for 400 tons. There was a reduction in the need of crushed aggregates, and also 4,000 tons in excavation and discarded soils. So this meant 20% savings compared to the conventional solution. The conclusions show that the storage time does not really affect rigidity and increase of strength, and actually curing time produces an increase in rigidity because of the loss of moisture and the reaction between the additive and the residual asphalt in RAP. The behavior of the asphalt is, and the deflection is very good to excellent, and we retrocalculated that we have a similar, or we confirmed the data from the lab. The climate effects do not have an influence on the good behavior of the asphalt layers. There's reduction of new materials and 20% reduction of costs. Here you have two links where you can go and check the complete paper developed by Engineer Wilson and the article that was published with our results. Thank you very much. Thank you, Pablo, and thank you to PIARC and the Argentine Association.
Bien,
Excellent. Thank you to all the presenters. We are well in time, so let's go now to the Q&A session. The first question is for Mario and Damián. I don't know, are you available for answering the questions? Am I missing one of the presenters? Well, the question says that having into account the challenges listed in the use of RAP in Argentina, have you thought about doing real-scale APT tests in our country? And I will start answering that. Mario have already said that Mario has a real-scale test stretch, and the National Road Administration has also requested for a piece of equipment to work with this type of materials to do these tests. We cannot.
Vamos a ver si avanzamos con la siguiente pregunta.
Let's see if we continue with the next question.
También es para Mario.
The next question is also for Mario. But we are here. So let's go back. The question was, Mario, taking into account the challenges for the use of RAP in Argentina, have you thought about doing APT tests in our country? Yeah, of course. As I said during my presentation, given some logistic reasons, we were not able to start our experimental stretch with a combination of warm RAP. As you know, the use of half-warm or warm mixes in Argentina has a 10-year experience, but the fact of combining a special mixture RAP combined with warm RAP is something new that we want to do. So once we have the data from the test stretch, we would complete our presentation with the data coming from that test. Next question is, what's your opinion on the reuse of CAT-12 or S12 with M3 mixtures for manufacturing MAC F10? Considering the discontinuity equal or lower than 10, or so that's quite a complicated question, but thank you for the question. But of course, any type of mixture can be potentially used as raw material, or the RAP from that mixture can be used as raw material for a new asphalt mixture. If we are talking about RAP coming from a mixture that has modified asphalt, whether it's dense or semi-dense, it should be evaluated for future use. As to compliance with specific granulometry in F10 or MAC, we should of course evaluate RAP granulometry, and for that it's important to consider the representative nature of that RAP, and it would depend on the piece of equipment used for the milling. And so based on the resulting values of those RAPs, it may be used or not at certain rates so that it would not have a negative impact on the mixture, but everything could be potentially used. That's why it is important to incorporate the RAP design or the RAP project in the request for proposals, how I'm going to do the milling procedure to get the RAP. That's part of RAP management. So why are we delay in our test? Because the idea was to take advantage of the RAP from the same work site where we are working on the test. But as you say, this just comes from the project. If the project says you need to start a milling process and reuse what you get from the milling process into the new road, that would be ideal. Yeah, it's a good message. Next question. Very interesting presentation, and the question is, what type of curing are you considering during the design of asphalt mixes HWMA, and whether it's different depending on dense or open asphalt mixtures? I think that this is for Luis Miguel. No, for me, for Curro, I guess. Yes, because it's talking about curing, so it's referring to emulsions. So I also have that question about curing. I think that both of us can elaborate on this because we have referred to that in our presentations. I think it's for half-warm mixes with or without milling production, and since this can be applied to different temperatures below 100 degrees, you need to consider a curing method that should be followed up in the lab to try to reproduce the humidity content in the plant. As to mixture times, you need to find out which are the right ones, and experience tells us that may be between 60 and 120 seconds. If the cores for volumetric analysis and for water safety are compacting, and I think that's the key of the issue, whether they are compacted with a rotating compactor. But we are not talking about just one type of mixture. We are talking about almost all type of mixtures that we may have with the different granulometric compositions. So if the presence of emulsion is the only common element, granulometry is highly variable, so we require to have a specific analysis of each one of these types of mixtures. We have certain reference values. I invite the person who has made the question, please, if you can give me that person contact information, because I can refer the person to the monographies prepared by ACETEP that already has a lot of information, monographies and exhibits describing how to take right samples. Alejandro Vicio is the person that made the question, so he's a good friend, so I would provide him with that information by myself or through the institution. So if he wants to get more information about that question, then I think, Luis Miguel, what's your opinion? In the case of emulsion, what we want to do with curing is to see whether at the lab we can observe the effect of the recycling binder or additive, and if we have residual asphalts in RAP. In our case, for dosing, we follow the recommendations of the ARRI. So the cores were preserved at 70 degrees for 24 hours, and 60 hours, 60 degrees, 24 hours. But at the second stage, where we had implant production, we collected the sample to assess the storage time, we followed the Briessinck recommendations where we have 40 degrees for 72 hours, because we had certain experience working with foam recycling, and we wanted to compare the results of this emulsion with the results we already had with foams. That's why we had kind of a hybrid solution. Okay, next question for Francisco. Which were the humidity rates of wrap at the time of making the mixes? I don't exactly know which were the values, but under proper storage conditions of those wrap materials, should have a preheating stage that cannot be done with other type of recyclings. And I have also said that the finer fraction is much forward in the drying drum than the coarser, and both are going to end up in the mixer with emulsion that will be the binder to envelop all the fractions. I think that humidity is not relevant in normal use conditions. If you have a storm and that wrap stockpile will be soaked in water, situation will be different. But the wrap is going to go through a preheating process hot enough to eliminate or evaporate any type of humidity that may be there. Of course, always the recommendation is to cover the wrap stockpile, whether it's half warm or hot. It should be covered. And what type of emulsions to use in warm?
Y bueno, me retrotraigo un poco.
Warm mixes. So, referring to the previous question, I would say that it depends on the design of the mixture. We are used to the fact that binders are highly standardized. And here we're not just talking about different types of mixtures. We are talking about the whole range of granulometries we may have. And we need to learn and we have to learn to accept that behind an emulsion mechanisms or binders mechanisms, we have a know-how. We need to apply that type of emulsion with the viscosity or penetration required by the final application. Because of the traffic volume, by the use of the wearing surface, the breaking point of the emulsion would be related to the amount of fines contained in the mixture, whether it's open or dense, and it should guarantee that in the mixer during a reasonable point of period of time should be enveloped, should be wrapped. And so we cannot have a specific answer to that question because there are so many half-warm mixes as granulometries we may have. So we need to adjust that in a case-by-case basis. You know that this is the typical question we receive, so that's why I have my answer well prepared. So, Gabriel Fidel says, excellent presentation. It's just congratulations. There's no question in this case. And next question is cold recycled mixtures. How did you consider Marshall molding here if the maximum size was 31 millimeters? So you use 3/4, 3/4, or what did you use? Good question. We did the screening and we need to verify the values when we are doing that, because we are just allowing for 31 millimeters of recycling material. So we delayed a little bit the process. We checked that. We did a quite comprehensive study, so if you want to have more details, you can check the whole presentation. So we did all the tests, checking the 31 millimeters in the Super P cores of 150 millimeters of diameters. So we tested at the lab whether there was some disruption in the mechanical behavior. I could not show that in my presentation, but it's already in the paper. You can use a modified Marshall for over 25 millimeters. It's not usual. In Brazil, it's not very much well known that. Neither here, but it's in North America, and it's used for this type of situation sometimes. And I downloaded the thesis you mentioned in your presentation, and it's very complete, and I just recommend it. Next question for Luis Miguel. Whether you can provide the links to the papers. Yeah. Rafael made a question about the request. Yes, I think that the links are already in the presentation. Okay. Good morning, Darwin Castillo from Peru, and the question is the material after 28 days. How is the behavior at compression and deformation pressure, stress? We did not analyze that at the lab. We just analyzed the tensile strength and the resilience modulus. But in the paper, we did a test over 120 storage days, of course, under optimal lab conditions, in very well tight close barrels and drums where the humidity was preserved and temperature also was preserved at 20 to 30 degrees. But so these show no impact or negative impact as regards the increase in resistance or strength or of the material. But another parameter that was checked up to 540 days of the stretch was the cross-sectional profile, and we were able to see the highest values at 4 millimeters. But of course, it was a left lane with a lighter and faster traffic. Of course, the question says, I understand that they are experimental stretches, but I would like to see what's the actual values and the maximum allowable figure for your country. So I'm not sure what the question is referring to. In the case of Brazil, the National Infrastructure Department has made an effort to update the standards for hot and cold mixes, and certain cases cold is limited to 50%, and as this was a state-owned road, we got to 100% because we worked together with the regulatory agency to approve 100% reuse. And this is a solution that is being analyzed by the licensee in some other similar projects. As regards to Spain, for many years, over 20 years of cold recycling with on-site emulsion. This is standardized in Spain with updates and continuous updates and reviews. Hot mixed recycling is being reviewed now in order to increase percentages and to consider using that in the wearing surface under certain traffic volumes. And I can say, at least I'm not in the technical office of the ministry, but I can say that they are highly committed to increase the recycling rates and the use of recycled material in the manufacturing of new bituminous mixtures. So excellent. And to conclude, Carlos Fonseca Rodriguez says congratulations to the three of our presenters. And what's your opinion as to the RAP percentages in each of the different techniques, cold, warm, and hot, limits and trends in the use of RAP? So we should start all over again, but just if you can give us a brief answer in 30 seconds. Mario? So first, I would just say that in Argentina, as I mentioned before, we have requests for technical proposals for hot mix with the limitations that I already described, but in the permanent asphalt committee, we're working in a specification project for in-place mixtures with foam, and we and with and also we are working on specifications for the use of RAP. As final comment, and before giving the floor to my colleagues, I'd say that the premise is we should use RAP, we should recycle. If possible, at the percentage allowed or possible, but I think that the world trend goes to conservative use of RAP, 25-30%. The US is an example. There's no state in the US that manages over these percentages, but RAP should be used at any rate, and that's the message. At any temperature also, with any technique. There's already technologies available to work with RIP at any temperature, and since we have run out of time, I will close this panel here. Thank you for your presentations, and we will go now to the closing of this PIARC seminar on the use of recycled materials in payments. Thank you very much.
Good morning, everyone. We are coming to a close in this international seminar for use of recycled materials in pavements from Technical Committee 4.1 of the World Road Association. And now we've come to the end with the conclusions. We have Mario Jair in the Pavement Technical Committee and the representative from Argentina in the Committee 4.1, Margo, the president of the Technical Committee of PR, and Maria Berretta, the president of the Argentinian Road Association. First, we're going to hear Mario with a summary of the conclusions of this seminar. Thank you, Federico, for the presentation, for the introduction. And first of all, I would like to thank everybody. When I was nominated in 2019 to be the representative from the Argentinian Road Association and the Argentinian Road Administration before PIARC, I went in 2020 to Europe, and one of the objectives at that point was to bring this seminar so that Argentina would organize it. And here we come to the second thanks, because Gina Ahlstrom, Miguel Gutierrez, and the English-speaking representative of the committee accepted this idea and supported and seconded the Argentina as a candidate for the organization of this seminar. But with the pandemic, we had to change the organization and do it as a virtual event. We thank everybody for the interest generated by this seminar, because we've had more than 15 people participating, 1,500 people participating, and that's very good, especially if we take into account that people are a little bit tired of virtual events, and also because of the number of virtual events that we have worldwide because of the pandemic. There were more than 65 countries participating. Not all of the countries appear here, but Latin America and Central America and the United States had more than 1,300, and then 200 more participants from some countries in Europe, and Australia, Bangladesh, Thailand, Slovenia, Slovakia. Many corners of the world were represented and had participants in this seminar. So thank you very much. We've had 17 technical presentations. 9 of those, almost half of them, as per the PIARC requirement, were representatives of the Technical Committee 4.1, 2 from Spain, France, Italy, Norway, Portugal, South Africa, Switzerland, and the USA. So that shows the wide range of experiences that we have shared, and take into account that many of these experiences are going to appear in the collection of case studies that Margo mentioned the first day, or 8 local speakers or regional speakers, 5 from Argentina and 2 from Brazil and Uruguay. And there were 9 presentations about recycling with asphalt binders, and 8 presentations about cement recycling and other types of materials such as plastic waste or reclaimed materials. I also want to thank the authorities of the Argentine Association of Roads, especially Federico and Hernan Ramirez, who were key to the organization of this Congress, and everybody supporting the organization, the technical people, also the interpreters are doing a magnificent job as usual. And again, thank you everybody for being here, for participating with us, and we hope to see you again in our next events. Thank you. Thank you, Mario Jair. Now we're going to hear a few closing words by Mario Briessinck, from the President of the Technical Committee 4.1.
And good afternoon, everybody. I'll be very brief. I'd like to start with congratulating the Argentinian Road Association for organizing this international seminar. One of the goals of a PIARC seminar is to exchange knowledge between the international PIARC community of the technical committees on the one hand and the regional road community on the other hand. And this seminar on pavement recycling clearly reached this goal. So mission accomplished, let's say. The Q&A sessions were filled with questions for more details and extra information. So I think it was a subject for a seminar that lives among the South American road community. And even though the interaction was not as interactive as could be in a face-to-face seminar, this online platform made it possible to reach out to a much broader audience, as Mario just said, which reached very far across the borders of Argentina and even outside the American continent, and making it a truly international seminar. I'd like to thank especially all the speakers for their interesting presentations, both from Argentina, Uruguay, Brazil, and from the Technical Committee 4.1 on pavements. And I hope that these presentations may inspire you to apply more recycled materials in your pavement structures, and that you're convinced that it can be a good material, and that with using these recycled materials, the same performances can be reached as the use of virgin materials to design a durable and a sustainable pavement, be it as a base layer, be it as an asphalt pavement, or be it as a concrete pavement. So thanks again. Thanks everybody for attending the seminar. Normally I would say have a safe trip or a safe flight back home, but I think nowadays everybody just has to switch off their computers and they're home again. So let's finish by saying enjoy the rest of the day in the week, and maybe until we meet again, hopefully in a live seminar or congress later during this PIARC cycle. Thank you.
Muchas gracias, Margo Briessinck.
Thank you, Mr. Briessinck. And now we are going to hear Nicolas Berretta, the president of the Argentine Association of Roads. Good afternoon, everyone. Today we are closing this international seminar of Technical Committee 4.1 for Pavements of PIARC, the World Road Association, organized by the Argentine Association of Roads as part of the Argentine Committee for use of recycled materials in pavements. For 3 days, we have had a debate and knowledge transfer discussing technologies. I want to thank the World Road Association and PIARC for enabling us and allowing the organization of this event by Argentina, which had a massive participation. I want to thank the specialists from Argentina and abroad that participated in this event, sharing their knowledge. I want to thank the moderators and coordinators dealing with each of the sessions. They were very good. We also want to thank our sponsors that have been with us for these 3 days, the National Road Committee, Coveno, Shell Bitumen, and Oholz in Argentina. Thank you very much to all of the participants and hope to see you soon. Thank you, Mr. Berretta. And with this, we close our international seminar for use of recycled materials in pavements, corresponding to Technical Committee 4.1 of PIARC. Thank you for your participation. And let me remind you that in the platform lobby, and you will have the survey for you to complete, and you will be receiving it by email too, so that we can improve and enhance our